In this problem, we are continuing the setting that we first modeled in problem 12 in section 4.1. There are 3 springs, 2 masses of mass m, and the spring on the left has spring constant k, and the middle one has spring constant 2k, and the spring on the right has spring constant k. We modeled this as a linear system with 4 variables, setting x3 to be the derivative of the first displacement, x4 to be the derivative of the second displacement. And here I've written a for k over m so that I don't have to write k over m over and over again. And we found when we did that problem that x3 prime was minus 3ax1 plus 2ax2, and x4 prime, the velocity, or the rate of change in time of that displacement, is 2ax1 minus 3ax2. Now the initial conditions that we're considering for this system are this. The object on the right is pulled to the right by 1. The object on the left is left at its rest position, at its equilibrium position, and then the system is let go. In other words, there's no velocity imparted to the objects at the beginning. And so x1 is the displacement of f, is 0. x2 is the displacement of g, is 1. And there's no velocity, so x1 prime at 0 is 0, which means that x3 at 0 is 0, and x2 prime at 0 is 0, which means that x4 at 0 is 0. So in vector form, the vector we're solving for is the vector 0, 1, 0, 0. And we're going to solve this system using a matrix. The matrix is going to be a 4x4 matrix. This is a first order system with 4 variables. It's linear in the variables. This is the system that we're trying to solve from that 2-spring example. Notice the first row says that x1 prime is equal to x3. The second row says that x2 prime is equal to x4. The third row says that x3 prime is minus 3a times x1 plus 2a times x2. And the fourth row says that x4 prime is 2a x1 minus 3a x2. All right, the characteristic equation for this matrix is the determinant of the matrix minus lambda times the identity is equal to 0. Let's expand the determinant, just reminding you how this goes. So I'm going to expand the determinant along the top row because I see a number of zeros, which is nice, and a 1, which is at least better than something more complicated. And so I have minus lambda times the determinant of this 3x3 over here. And so minus lambda, and in here I'm going to have the determinant of this 3x3. So let's see, I have minus lambda, and the subdeterminant here is minus lambda and minus lambda. So altogether minus lambda cubed. And then I have a minus sign attached to this 0, which of course doesn't contribute anything. And then a plus sign attached to this 1. And the subdeterminant is going to be this 2x2. So plus 1 times 2a times 0 is 0, minus lambda times minus 3a is minus plus lambda times 3a. And so I get minus lambda times 3a. And that's from expanding this minus lambda and this submatrix. Now let's this 0 contributes 0. 1, the 1 gets a plus sign because we go plus, minus, plus. So the 1 gets a plus sign, and we are now ignoring this row and this column. And so we have 1 times the determinant of the 3 by 3 that is left. We have 0 with a plus sign, which gives nothing. And then we have minus lambda with a minus sign, so that gives plus lambda. And the subdeterminant here is minus 3a times minus lambda, which is plus 3a lambda, and then 0, so that's this term here. And then moving on to this 1, which gets a plus sign, we get the subdeterminant of this 2 by 2, which is minus 3a times minus 3a, which is 9a squared, and then minus 2a times 2a, which is minus 4a squared. When you write all this out, you get lambda to the 4th plus 6a lambda squared plus 5a squared. This is a 4th order equation, so even though there is a formula for 4th order equations, it's a very messy formula. But lucky for us, the only terms that appear are lambda to the 4th and lambda squared, and so this is actually quadratic in lambda squared. We have lambda squared squared plus 6a lambda squared plus a constant is equal to 0. So we can solve this using the quadratic equation. Solving the quadratic equation, we get that lambda squared is minus 5a, or lambda squared is equal to minus a. Now remember, a was the spin constant over m, and so that's positive, which means that lambda 1 is either plus or minus the square root of 5a times I, and lambda 2 is either plus or minus the square root of a times 1. Now I'm not going to worry about whether lambda 1 is plus or minus, because we're expecting oscillatory solutions, sines and cosines, with a particular frequency, and so plus or minus doesn't make a difference, just changes the coefficients of the vectors. So let's look at what we have for an eigenvector with lambda 1 equal to the square root of 5a times the square root of minus 1. Plugging this back into the original matrix, I get that x3 is the square root of 5a times ix1. x4 is the square root of 5a times ix2. And then looking at the third row, I get that minus 3ax1 plus 2ax2 is equal to the eigenvalue times x3. Now there is a 4th row, but I didn't write it down because if there is really an eigenvector for this eigenvalue, then there should be a free variable. So rather than writing it down now, we can just check later that the vector we got really is an eigenvector. Moving right along, let's look at the third equation. It said minus 3ax1 plus 2ax2 is the square root of 5a times I times x3, which is the square root of 5a times I times x1. This gives minus 5ax1. And so since we have a free variable, let's just pick something. I'm going to take x1 equal to 1. Looking in here, this says that 2ax2 is equal to minus 2ax1, so x2 is equal to minus 1. And plugging 1 for x1 into the equation for x3 and minus 1 into the equation for x4, we get these values. I'm going to write this up as a vector, and that vector is going to be multiplied by e to the square root of 5ait, which we interpret as cosine square root of 5at plus I sine square root of 5at. Again, we're expecting oscillatory solutions, and so this is not a surprise. Here's the eigenvector written as a vector. x1 is 1, x2 is minus 1, x3 is the square root of 5a times the square root of minus 1, x4 is minus the square root of 5a times the square root of minus 1. And if I take e to the eigenvalue t multiplied by this vector, I get this vector, which I've written in terms of its, everything in here does not contain the square root of minus 1, and everything in here contains the square root of minus 1. So, for example, I get 1 times cosine square root of 5at in this component, and then I get I times sine of the square root of 5at times 1 in the component that involves the square root of I. Let me just read these through quickly in case they're not so visible. Minus cosine minus the square root of 5a times sine plus the square root of 5a times sine, and then in the component that involves the square root of I get sine minus sine the square root of 5a times cosine minus the square root of 5a times cosine. And remember from linear independence that the part that does not involve the square root of minus 1 is an eigenvector for the original matrix, and the part that does involve the square root that is multiplied by the square root of minus 1 is also an eigenvector. So in fact, we found two linearly independent solutions to the original system. The first part of this e to the lambda 1t times u1, and the second part, just without the square root of minus 1, is also a solution to the differential equation. So we have two solutions from this one eigenvalue. For the second eigenvalue, the square root of a times the square root of minus 1, we find the eigenvector 1, 1, square root of ai, square root of ai. Again, we have a free variable, so I've chosen x1 equal to 1. And we're using e to the square root of ait as cosine square root of at plus I sine square root of at, and multiplying this by this vector, again separating into the horizontal part in the complex plane and the vertical part in the complex plane, the real and imaginary so-called things. We have cosine times 1, we have cosine times 1, we have minus square root of a times sine, we have minus square root of a times sine, and then in the part that includes the square root of I have square root of a I times cosine. Over here, I have square root of a cosine times I in the fourth component. In the first component, I have I times sine at times 1. And in the second component, I also have I times sine at times 1. So again, we know that this vector is a solution to the system, and that this vector is a solution to the system, and they are linearly independent, which you can easily see. These are also linearly independent from the first two solutions that we found. So now we have 4 solutions to the system that are linearly independent. Let's put all of this together as best we can. So we have the general solution, constant times the one eigenvector, constant times the second eigenvector, both of these corresponding to the oscillatory factor from the square root of 5a times I in the eigenvalue, and then C3 times the third eigenvector, third solution, and C4 times the fourth solution. Those two coming from the oscillatory solution corresponding to lambda 2 equal to square root of a times I. And then the initial condition that we wanted was 0, 1, 0, 0, at time 0. So let's see what that gives us. At time 0, cosine of 0 is 1, and sine of 0 is 0. So for example, in the first row from this, I get C1, C2 does not appear, plus C3, and C4 does not appear. So in the first row, I get that C1 plus C2 is equal to 0, or that C2 is minus C1. In the second row, I get that minus C1 plus C3 is equal to 1. And in the third row, I get square root of 5a C2 plus square root of a C4 is equal to 0. And finally, in the fourth row, I get that minus square root of 5c2 plus square root of a c4 is equal to 0. Solving these, you can see that c2 and c4 have to be equal to 0, and we said that c3 was minus c1. So, and it turns out that to get 1, I need c1 to be minus a half and C3 to be plus a half to get this 1 in the second coordinate. So that's our solution. Our solution is minus a half times this, plus a half times that.